So what do you do if you don't have a clue what the population mean is? How do you come up with it? How do you calculate it? Well, what you're going to end up doing is taking a sample and assuming that's close enough. But we all know that 1 point is not a good estimate. So we want to feel better about it. And so it's easier to come up with, I like to always say, like a best and a worst case scenario. And so what do I mean by that? Well, if I'm going to judge my salespeople and I say that the $1 million mark is what I expect their sales to be, am I going to get mad at them if they're at $995,000? Or am I going to be really excited when they're at 1.1 million? Am I going to be really excited when they're at 2 million when they said the mark was 1 million? Yeah, probably. But the truth is, data varies. Samples vary. So we can never just look at 1 point and assume everybody's going to do that. To give a sports analogy, which I hate to do, but I'm going to do it anyways. And a lot of us play, I'm terrible at golf, probably the worst golfer you ever see. That's why I keep my clubs in the garage most of the time. But I know that when I hit a ball, I might average certain yardage, 200 yards, let's say. I'm really not good. But the truth is, I might be 170 one time, 230 the next time, and I'll vary from that. But overall, it'll be that. But I want to know basically, well, what's my best case scenario, worst case scenario when I'm shooting a ball, when I'm on the golf course. In terms of business, we want to have benchmarks, and it's easier to have a benchmark with a high and a low as opposed to just one single value. So, if I want to estimate costs for the upcoming year, I want to do it with worst case scenario sales, not the average, because if I do that, then 50% of the time I'm going to lose money. So you go with worst case scenario. That's what we're trying to do when we're looking at confidence intervals in this chapter. And when we do that, we're going to do it basically 3 ways. There's 3 on there that we're going to care about. We're going to care about we're going to estimate the population mean if we know the standard deviation. Now, how often do we know a population standard deviation? Not often. The only time we really do is if we are using historical data. The second one, which is the more common one, is when you do not know anything about the population. You don't know the population mean, you don't know the standard deviation, so you're going to use your sample as an estimate for your population, including the standard deviation. And then we can obviously determine sample size, but then also on here we can look at population proportion. So those are the different things that we can look at in terms of this chapter. The calculations are really easy. I'm going to fly through those in this, so I'm not wasting your time. But what you need to know is kind of what that really is telling you. So what we do is we come up with a point estimate. Point estimate, as we know from the last chapter, is a sample mean. When I look at that sample mean, is that a good estimate of the population? Well, what we can do is give ourselves a margin of error. And we usually do it based on what's called a confidence interval, which means that if I say I'm a 95% confident, that means that about 95% of the time, I should be, this sample should include the population mean. So if you're outside that, that means that our sample is pretty much drastically different than what we were expecting. Now, when I say population mean in this case, in most cases, we're now to the point where we're thinking, a population mean might just be a sales target. It might be, a benchmark. I want my school to average a 30 on the ACT. That kind of thing. That's a target that somebody would be shooting for. And then in the end, based on a sample, you can say, well, is that 30 even close? Is it approachable? Are we off just because of randomness, or are we off because we're really that bad if we scored a 28 or a 27 as a school? Things like that. All right, so let's get into the examples. Again, looking at the margin of error, I'm going to go straight into the example here, and then I'll show you the formula as we do that. Here are the most common confidence intervals, and 95% is what we use almost all the time. if you have a 95% confidence interval and you're using z-scores, you know your corresponding z-score is 1.96. Now, where did that come from? Well, let me tell you this. If you think about 95% confidence interval, if you look up 97.5 in your table, you get 1.96. Now, let me show you what that means. So if I talk about a 95% confidence interval, that's what this includes. That then means on this side is 0.025, and on this side is 0.025, which means from here over is 0.9750. So if I look up 0.9750 in my table, I get 1.96. So that's where that value comes from. Okay, so if I had a calculation, again, I want to get right into the problem here. Let's go right into it. There you go. And we're looking at Discount Sounds has 260 retail outlets, and they take a sample of 36 of them and find out that the mean income is $41,100. Well, that's a sample of 36 of the 260. So is that good? Is it bad? What does that tell you about your data? Well, if the population standard deviation is estimated to be 4,500, so we've got a known population standard deviation, and the confidence coefficient to be used in this case is 95% or 0.95, let's come up with what our best and worst case scenario would be. So here's the calculation. Let's go over here and take a look. So first of all, I'll write over here our different values. So based on those values that we have up here, let's come up with that calculation. So when we're talking about mean income, that's a point estimate, okay? So that point estimate is going to be our sample mean in this case. That's what we're going to use. Now with that, we want a best and a worst case scenario. And the best case scenario, because mean income, we want more of it, is going to be something over here that is a plus value because it's going to be more. And then this way, it's going to be less. And so the margin of error that we're going to put here, this is your error that you're willing to accept here, is plus or minus the sample mean. So our calculation then ends up being plus or minus our z-score, because again, we've got z-scores on a bell curve, times, remember that thing called standard error? Standard error. So in this case, we're talking 1.96 because we're doing 95% confidence interval, times 4,500 divided by the square root of 36. So you get this and you subtract it from 41,100 to get your value over here, and you add it to get the value over here. And so let's see that. I think this calculation is actually pretty easy to do. And so let's take a look. When we do that, we get our margin of error to be 1,470. When we add and subtract that from 41,100, we get 39,630 as our worst case scenario, or our lower limit, and then our upper limit would be 42,570. So that means $39,630 42,570. 9570, and that means in between here is 95% of all possible values. So that should make you feel pretty good that you're 95% confident that your population mean is between those values. And so if it's not, then whoops, we've got a problem. If it's way out here, then we are obviously significantly different than the mean according to that. If we're way up here, that means we're also significantly different and it's a lot higher, and that would be a good thing, right? To have more income than less income, I think that would be a good thing in this case. So that's what you do when you're doing this for a known standard deviation. You'll use Z, and the margin of error is calculated using Z times standard error. Okay, we can also just take a quick look at what it would look like if we did this in Excel. There is a confidence formula or function that allows you to come up with your margin of error, and then you have to add and subtract it to get the correct values, and that's what you see here. Also, if you want to just look, if you were to instead want to do a confidence level of 90%, then instead of 1.96, you would use 1.645. And if you want to do 99%, you would use 2.58 instead of 1.96. And so it would just create a larger interval estimate at 99% than at 95.